In this video, we are going to talk about 7.6, double integrals over rectangular region. In this section, the goal is to evaluate both indefinite and definite of double integrals. Just like we had differentiation that can be differentiated twice, 3 times, or 4th time, same thing can happen for the integrals. We've been used to integrating just once with single integral. Now you're going to see double integral. So if you're looking at a couple example that is following, take a look at this. You see the double integral. So you're going to integrate it twice. Now, in terms of integrating, look at the function. There is x value and the y value. So kind of like when you did implicit differentiation or partial derivative, we're going to integrate it with what's given first, dy term, respect to y, and then after this, we are going to integrate it respect to x. Just like when in algebra we start with the inside out like a parenthesis, so we integrate it with the dy term first, dx term in this case. So let's start with a couple definition and a theorem. So first definition, double integral. The double integral of a function f of x comma y. Notice now function has two variable involved. And then this will create a rectangle region bounded by certain x value and then certain y value. So we will associate x as a to b and then the y value c to d. So it's gonna create a region. And recall when we first introduced integral, it represents the area. So we are going to be also finding the area. Now, this is how we formally define double integral over some region defined by x between AB, y between CD of that dA. A represents the area. So take a look at the definition. First one, you have dy first, and then second one, you have a dx first. Notice, here's a key thing that I want you to notice. If you look at the definition here, you're gonna see that y, if you integrated y first, you're going to use the y value, CD. Okay? Do not mix up A, B, and CD. And then afterwards, you're going to integrate it x term, A and B. So if you start the x term, you want to use A to B first. And then after that, you are integrating respect to y, so you're going to use CD. So look at this one, the order does not matter. You're going to have an equal result. So you can choose to integrate with dy first, the y term, or you can integrate it with dx. You're going to see that in example, we are going to confirm this definition on example 2. So example 2 will integrate it both times and then see that you get exact same number. Now, one thing that I want you to note, when you integrate it respect to y, I'm just going to elaborate this one. When you integrate respect to y, right? Because dy, you will treat x term as constant. Okay, so any x term that you see when you integrate it, you're going to treat it like a constant. Then dx, this means you integrate it respect to x. So second time when you integrate the second integral, when you integrate respect to x, then you will treat y term as constant. Okay, vice versa for the second one. This one dx, you're going to treat the x term as a y term as a constant. dy, you're going to treat x term when you integrate. Second one, average value over rectangular region. This formula looks very similar. Recall in Math 121, in average value theorem, you had 1 over b minus a f of x dx, where a to b. So same format. So this was average value theorem from Math 122. So it looks very similar concept. You have 1 over b minus a times d minus c. Again, these are coming from your x and y term. So x are your a and b, and then the y's are your c and d. And then you can decide how you wanna do the double integral. Sometimes integrating y term is better. Sometimes integrating x term first is better. So you have two options. Commutative property, both results will give you same, so you don't have to do it twice. Pick the one that you like most and then integrate it. Last one is a volume. Volume is volume over a rectangle region. Again, define it as x between a to b, y define c to d. Then the volume of solid by group volume of the solid formed by graphing f over the rectangle is given by f of x dA. So let's jump right onto the first question and begin our very first double integral. Notice first dy. Here you're seeing the dy. So I'm going to use, I'm just gonna color code it to the and then x terms are these, right? Again, inside out, we are going to integrate this one first, respect to x, respect to y, then respect to x. Respect to y means x variable is constant. So this whole thing is your constant. So how do you integrate? How do you integrate y to the fourth? Raise power divided by new power. So you're going to have negative 2 to 3. And then this portion right over here will be, so this whole thing is constant, raised power divided by new power. Now here you're integrating. Now you can do this, but I sometimes like to write it this way to letting me know that zeros and 4, we are plugging into the y term. Okay, and then let me do it this way. Oops. Let me rewrite it a little bit better. Y 0 to 4, and then integrate a second time respect to x. Let's simplify here a little bit. So reduce down to 4. So 4x cubed y to the 5th power. Only plug it in 0 and 4 to the y, because remember I just highlighted this 0 to 4 is the y variable value. Okay. So I'm integrating this, and then you now plug it in. So negative 2 to 3. We haven't integrated second time yet. Simplifying this, I have 4 cube. I'm sorry. X term. Plug it in to the y term, right? This is why I use highlighter. Only plug it into the y. So 4 to the 5th power minus 4x cubed 0 to the 5th power dx. Keep going, simplifying. This term is just 0. And then I'm going to have 4 to the 5th power. 4 to the 5th power, that's 1024 times 4, 4096x cubed. 4096x cubed dx. Then you have x term surviving, and that's good because these are all associated with x terms. So now you integrate with respect to x. Same thing, this is a simple integral. So we are going to raise power divided by new power. So 4096 x to the 4th power divided by 4 from -2 to 3. So 4096 divided by 4 will give you 1024 x to the 4th from -2 to 3. So we have 1024 times 3 to the 4th power minus 1024 -2 to the 4th power. Simplifying, I'm getting the final answer as I put everything into a calculator. I get 66,560. Done. Okay, so you just have to be careful. Do not mix up the number. Take a look at the order. So dy, so you plug it in these number with the y term and then integrate it second time with the dx. So very similar concept. We can differentiate once. We can differentiate function twice. We can differentiate something third time. So same thing. I can integrate it once, twice, 3 times, 4th time, whatsoever. Okay. Let's do second problem. Very similar. This time, I'm going to do both iteration over this double integral. So notice that it's vague. It's just say, here's the region, and then dA means differentiate the area. So this is where we confirm the first definition. We are going to do both times. First with dy, and then second one with dx, and then we are going to see that they are going to give you exact same number. Okay, so let's integrate it both times. So the first one, I'm going to start with this one here, my first definition, dy dx. So integrating with respect to y term first. So here's the first one. So again, let me use the highlighter. I'm going to use x term for the blue and then y term for the green. Okay, so the first setup will be respect to y term first. So that means x here is where it goes, and then the y 0 to 5. My function is this one over here, x cubed y cubed dy dx, right? dy dx, because I want to integrate it y term first. Let's also highlight so that we don't get confused. And then this is for the x. So we'll repeat exact same thing as what we did in the first one. I'm going to integrate this part respect to y. That means x term is constant. So this is a constant. So constant y to the 3rd. So raised power divided by new power. So that's a very simple one. So -4 to 0. Okay, and then so this is constant raised power divided by new power. Y equals 0, y equals 5. You do not have to write exactly y equals 0. Some textbook does use the y term to letting where to plug it in. Okay, dx. Again, these are where my y term. 0 and 5 is the y variable value. So let's plug it in. Over here, I see that I have that 1/4. So technically that can be taken out of the integral because it's a constant. So I'm going to pull that to make it simple. 1/4 is taken out. -4 to 0. And then you have x cubed y to the 4th, y equals 0, y to the 5. And then whole thing dx. You can keep it 1/4, but I just like to have the fraction taken out. So plug it in. 1/4, -4 to 0. Here, again, these are my y values. So I'm going to have x to the cube, 5 to the 4th, minus x cubed, 0 to the 4th power, dx. This part disappears because it's a 0. So I'm going to have 1/4, -4 to 0. This 5 to the 4th power is 625. So I'm having 625 x cubed dx. Okay. All right. Now, let's keep going. You know that I can also take this one out of the integral because it's a constant. So let's do that. So 625/4, -4 to 0, x cubed dx. And it's easy integral. So 625/4. Now x to the 4th over 4 from -4 to 0 dx. Oops. I integrated, so dx disappear. So I'm going to have 625/4. I have 0 to the 4th over 4 minus -4 to the 4 over 4. 625/4, this part is a 0 minus 4 raised to the 4th power. That's 256/4. So this really is 625/4 times -256/4. So let's multiply this. 625 times -256, that's -16,160,000 divided by 16. So I'm going to have -10,000 as a final answer. Okay? So that's this first definition. So we got this first definition here, -10,000. Now I'm going to switch the order, integrated with the respect to x first, and you're gonna see that it's gonna give you -10,000. So let's check. So I'm going to add another page. So let's add a new page. Okay, same thing. This time I'm going to integrate it respect to x. So I'm going to have switched over 0 to 5, -4 to 0, x cubed, same function, but dx, dy this time. Okay. We already know the answer should be -10,000. Let's use colors again. So x, I use blue highlighter, so blue for the x, and then green for the y's. I'm going to integrate respect to x first. That means y term is constant, so this part is a constant. So we have raised power divided by new power, so x to the 4th divided by 4. 0, 5 Here I'm going to have x cubed y to the 4th divided by 4. Here x equal negative 4, x equals 0, dy. So same trick, I'm gonna pull out the 1/4 outside, so it's simpler. And then I have x cubed y to the 4th, x equal negative 4, x equals 0, dy. Plug it into the x term. I'm going to have 0 cubed y to the 4th minus negative 4 cubed y to the 4th power dy. This term is just 0, so I have 1/4, 0 to 5. Negative 4 cubed is negative 64. With this negative, I'm gonna have positive 64 y to the 4th dy. Pulling out the 64 outside, so we have 64 over 4, 0 to 5, y to the 4th dy. 64 divided by 4 is 16. This one, raised power divided by new power, y to the 5th over 5, from 0 to 5. So I have 16, 5 to the 5th power divided by 5 minus 0 to the 5th power over 5. So I'm going to have 16, and then 5 to the 5th power is 3,125 divided by 5 will give me 625 minus 0. 625 times 16. Hold on. I get positive 10,000. Should have a negative. Let's see where I made a mistake. Let's see. Should have a negative. Looks like I made a mistake. Oops, I totally screwed up. I see where I made a mistake. This is why we want to keep track. Here, we are taking the derivative. I screwed up from beginning. I'm supposed to differentiate respect to x term first, and I actually derive with the y term. So I screwed up at the beginning. Let's redo it. Let's start over. Because I know that, see, this is a good thing. So I made a mistake, and I knew that my answer is not correct because I need to get negative 10,000. So that means you want to fix your mistake, and I did find the mistake. I differentiated with y because I should have an x to the 4th power. So let's fix this one. So let's, this should be, I'm gonna write it in red so you guys see that. X to the 4th y cubed over 4. So this part over here should be x to the 4th y cubed. Okay, that's where I screwed up. So here, I'm gonna erase this whole thing so that it doesn't confuse. So let's start over. My apologies. So 1 over 4, 0 to 5. So here I'm going to plug it in my x, so 0 to the 4th y cubed minus negative 4 to the fourth power y cubed dy. And that's good. I see that negative here. It's not going to make a positive, so I'm going to get negative 10,000. So that's a good sign. But let's keep going. 1 over 4, 0 to 5. This whole thing turns to 0. This part will be negative 64. Negative. So negative 4. Negative 256. So negative 256 y to the third power dy. Pulling out the constant, so you have negative 256 over 4, 0 to 5, y cubed dy. Negative 256 divided by 4 is negative 64. Integrating this, raised power divided by new power, 0 to 5. So we have negative 64, 5 to the fourth power over 4, 0 to the fourth power over 4. So I'm going to have negative 64. 5 to the fourth power is 625 over 4. Next one is a 0. This one is a 0. Okay, so negative 64 times 625 is negative 40,000 divided by 4. We get negative 10,000, which is exactly what we have with the previous page. So both order of iteration, you're going to get the same answer. Okay, so unless the problem told you to do both ways, you do not have to do it. You can pick if you want to integrate it x term first or y term first, and then you can kind of pick on that depending on how this function look like. Okay. All right, let's do find the average problem and then the volume. So we have average value over here as a second definition and then volume. And then I put one application problem, number 5. Okay, so average value. So I'm going to copy my function here. Okay, actually, let's do this. Okay, copy. So I have that handy, and then okay, let's paste it. Then I'm going to literally plug it in into this equation. So here are my x value 0 to 4, and then y value negative 3 to 1. So let's plug it in into the formula. 1 over 4 minus 0, and then d minus c will be 1 minus negative 3. Now here, we just saw on example 2, the order does not matter. You can differentiate it with the x first or the y first. So I'm just gonna differentiate dx, dy. Because we did we already did the dy problem first. So I wanna do this order. So I will iterate it. So negative 3, 2, 1. So dy is the second one, and then the x one is the first one. And my function is 3x squared minus 4y cubed dx dy. Okay. Now, can you switch? Yes, we just saw that it's gonna give you same result. Okay, so here 4 minus 0 is 4. That's 4. So 1 over 16. Negative 3 to 1. 0 to 4. Because I'm integrating the x term first, this y term is a constant. So this really is a constant. So this part is constant, and this is the one that we want to integrate. So raised power divided by new power. So raised power divided by new power. So I'm going to have a first term x cubed. This is a constant when you take the derivative respect to x. So I'm going to have 4y constant. You gain a power x. So let's switch out to make it pretty. 4xy cubed is what I'm having. 4xy cubed. X equals 0, x equals 4 dy. Okay. I'm going to delete this picture so we have more space to write. Okay, 1 over 16, negative 3 to 1. Now, if I integrate it and plug it in the number, I'm going to have 4 cubed minus 4 times 4y cubed minus 0 cubed minus 4 times 0 y cubed, which really is a 0, dy. So this is just a 0. So 1 over 16, negative 3 to 1. This part over here, 4 cubed is 64. Second term, 16y to the third power dy. Easy integral, term by term, respect to y this time. So 1 over 16. Over here we gain a power, so 64y. 16 divided by 4, because we raise a power divided by new power. So I'm having 4y to the fourth power from negative 3 to 1. Let's keep going. I am running out of space. So let me even make it smaller so we can all fit here. So 1 over 16, 64, 1 minus 4, 1 cube minus 64, negative 3 minus 4, negative 3 to the fourth power. Okay. Simplifying my first parentheses, this one here, I get 64 minus 4. And then this part here, I get negative 192 minus 324. Okay. All together at the end, if I simplify, I'm getting final answer as 36. Okay. All right, so just practicing, getting just familiar with integrating twice. Okay. Last topic, volume, finding the volume, and then we have one application problem together. Find the volume of a solid under the graph of a function over the given rectangle. So we are given the theorem from the textbook, the volume of a surface right over here. Double integral of the region, and then you have a choice. dy, so basically we are taking the double integral. So let's set up. My y term, my x term, and then you have a choice. So let's see, I'm gonna do dx dy. You can switch around. And then you have 4x plus 8y minus 7 is your function. Now, because you use x term, you can see that I am integrating dx then dy. The outer part is my y. Okay. So, derivative respect to x mean y term is constant. Okay, so I need to take the derivative. These are just constant. So -1 to 3. This part here, I have the first one. This is actually the x term, so raised power divided by new power. I'm getting the first one 2x squared. 8y, that's a constant, so you gain a variable, so 8xy. -7 is a constant, so -7x from x equal -2 to 2. And then dy. Plug it in all these values for x. So I have -1 to 3. Here, 2 squared plus 8 times 2y minus 7 times 2 for the first one. Minus 2 times -2 squared plus 8 times -2y minus 7 times -2 dy. Let's simplify. -1 to 3. This one over here, the first set, I'm going to have 8 plus 16y minus 14. And then the second parentheses, I have 8 minus 16y plus 14. And then whole thing dy. Let's simplify further. You have -1 to 3. This term, 8 minus 14, I have -6. So I have -6 plus 16y. Here I have 8 plus 14. That's gonna make 8 plus 14. So I have inside parentheses -16y plus 22, but I'm going to distribute this negative, so I have plus 16y minus 22 dy. Okay, you can even simplify further, so let's do that. But let me resize this a little bit. -1 to 3. I have 16 plus 16, that's 32y. -6 minus 22, -28 dy. Really easy one to integrate. Gain power divided by new power. So I'm having 32y squared over 2 minus 28y from -1 to 3. Okay, 32 divided by 2, that's 16. So really you have 16y squared minus 28y from -1 to 3. So you have 16. 3 squared minus 28, 3 minus 16, -1 squared minus 28, -1. So let's keep going. I have, if you simplify the whole thing, putting in the calculator, I get the final answer as 16. Since it's a volume, it's a third dimensional, you can really say cubic units. Okay. All right, one more homework actually, one more example, and then also this there are a couple homework problems with application problems, so this is a good practice. Number 5, if an industry invests X thousand labor hours, so we have again X, so I've been using the blue highlighter, so I'm gonna highlight blue, and then Y is a million, so X represent the number of hours, Y represent the money. In the production of n thousand unit of a certain item, then n, the production function, is given by n of x comma y, x raised to the 0.75, y raised to the 0.25. What is the average number of unit produced? You see the word average number of unit. So on top of double integral, we have this 1 over b minus a times d minus c, because that's the average. If there is no average, then you're just gonna do double integral, but you see the average number, so look for the keyword. So we are using the average formula. Unit to produce for the indicated range of x comma y, set up the double integral and evaluate it. So again, it's nothing different, okay? Instead of giving you like the formula like this, they just kind of phrase it, but you're doing the same thing. So let's set up one more practice. So my B is 20 and then my A is 10. So 20 minus 10. D minus C is 2 minus 1. Double integral. Okay. I just like to switch back and forth so you see the variety. This time I will evaluate a dy dx, okay? So if you're using dy dx, x term first. So I have 10 to 20, 1 to 2, and then my function n of x comma y. So my f of x comma y will be my function here. X raised to 0.75, y 0.25. Notice I used dy here, and then my x term is this. So I'm integrating dy, then dx. Okay, let's simplify. So this one is 20 minus 10 is 10. 2 minus 1 is 1. So I have 1 over 10. 10 to 20. 1 to 2. X 0.75, y 0.25, dy dx. Now integrating dy means x is a constant. So this part is a constant. So you just have plus 1 divided by new power 1.25. So if I'm integrating for the dy, I have 1 over 10, 10 to 20. I have x point 0.75, y 1.25, because I'm adding a power from y equal 1, y equal 2 dx. Let's pull out 1.25 outside, just like we did. So I'm going to pull out this part here. So that's going to be, that's on the bottom. So 10 times 1.25, so 12.5, 10 to 20. And then you have x 0.75, y 1.25, going from y equal 1, y equal 2 dx. So I'm going to plug it in these number to the y function. So 1 over 12.5, 10 to 20, x raised to 0.75, y is 2 raised to 1.25, and then x raised to 0.75, 1 raised to 1.25. dx. Let's simplify. So 1 over 12.5. Now I know 2 raised to the 1.25 is a messy messy number, so I just like to keep it. I don't want to round it too much yet, so I'll just keep it as 2 raised to 1.25. So 2 raised to 1.25 x 0.75. This is just minus x 0.75 dx. Now term by term. So let's add a new page. I will copy this one here. Okay, so dx, term by term, 1 over 12.5 raised power divided by new power. So my first term will be 1.25 x 1.75 because adding a power, right? So 1.75 minus x raised to 1.75 over 1.75 from 10 to 20. So 1 over 12.5, and simplifying their common denominator, so 2.2 raised to 1.25 x raised to 1.75 minus x raised to 1.75 over 1.75 from 10 to 20. Pulling out that 1.75 outside because it's a constant. It's on the bottom, so 12.5 times 1.75 will give me 1 over 21.875. And then inside you have 2 raised to 1.25 x raised to 1.75 minus x 1.75, 10 to 20. Okay, it looks a lot kind of messy, but it's we are getting there. All we have to do is now plug it in, evaluate. 1 over 21.875. If I plug it in 20, I have 2 raised to 1.25. That's 20 raised to 1.75 minus 21.75 minus 2 times 1.25 x, that's 10 raised to 1.75 minus 10 raised to 1.75 whole thing. This first set of parentheses, if I plug it in into the calculator, I round it to the 4 decimal place. I get 260.7247. This one, I plug it in the calculator, I get 77.5139, rounded to the 4 decimal place. Let's subtract, divided by the whole thing. Final answer, I get 8.375. So let's just double check. We are having a unit of thousands labor hour. So it's really not 8.375. It is about moving 3 decimal to the thousand plate, 8,375 units. Okay. All right, that's it. So we practice integrating double on the solid that is creating by rectangle. Now, next section, we are going to still continue to work on double integral over the more general region.